All right, so we've spent some time on the theory behind Kirchhoff's laws, right? Well, today is where the rubber meets the road. We're going to take a pretty simple circuit and just walk through it, step by step, from start to finish. You'll see exactly how these super powerful rules work in the real world. So let's get into it.
Okay, here's how we're going to tackle this. First, we'll look at the circuit challenge itself. What are we even trying to solve? Then, we'll use Ohm's law as our first step. After that, we'll bring in KCL. And you know what? We'll do a final check with KVL, just to be sure. By the end, you'll have a solid toolkit for this stuff.
All right, first things first, the circuit challenge. Before we jump into any math, and I mean any math, we have to understand the problem. We need to look at what's in our circuit and be super clear about what we're actually trying to find. Honestly, getting this part right makes the rest of it a total breeze. So what are we working with? We've got a 10-volt battery, and it's connected to two resistors, R1 and R2. One is 2 ohms, the other is 3 ohms. And see that spot where the wires meet? That's our junction node. That's going to be really important later. So what's the goal here? Simple. We need to find the current going through each branch, which we'll call I1 and I2, and then figure out the total current coming from the battery. And this right here, this is the whole key to the puzzle. You've got the main current flowing out from the battery, right? And then it gets to that node, that junction point, and it has to split. It's like a fork in the road. One part goes one way, the other goes another. The moment you see current splitting like this, a little bell should go off in your head that says, aha, I'm definitely going to need Kirchhoff's current law here. Okay, time to do some math. Our first step is to pull out the most fundamental tool we have, good old Ohm's law. We're going to use it to calculate the current in each of those branches, one at a time. So let's remember the absolute classic, Ohm's law. Current is just voltage divided by resistance. Now, here's something really important about our circuit. It's a parallel circuit. What does that mean for us? It means both of those resistors are connected directly to the 10-volt battery, so they each get the full 10 volts. That makes our first calculation super straightforward. So for that first branch, the one with resistor R1, it's pretty simple. We take our voltage, which is 10 volts, and we divide it by the resistance, which is 2 ohms. And boom, that gives us exactly 5 amps. Easy, right? That's I1, the current flowing through our first resistor. First piece of the puzzle, done. All right, on to the second branch with R2. The process is exactly the same. No tricks here. We've still got that 10 volts across it, and this time the resistance is 3 ohms. So 10 divided by 3, that gives us about 3.33 amps. Perfect. So now we have both our branch currents. We know how much current is going down each path after that split. Okay, so we've got our branch currents. Now let's apply KCL. We're going to zoom right in on that node, that junction point, because this is where Kirchhoff's current law is going to help us figure out the total current that the battery was pushing out to begin with. So think about it. If we know that 5 amps went down one path and about 3.33 amps went down the other, well, how do we find the total amount of current that came into that intersection in the first place? And the answer comes from Kirchhoff's current law, or KCL. It's really just a law of conservation. It basically says that whatever current flows into a junction has to be the same amount of current that flows out. You can't just lose current. It doesn't just disappear into thin air. And you know what? Applying this is incredibly simple. All we have to do is add up the currents that are leaving the node. So if 5 amps are going out one way and 3.33 amps are going out the other way, the total current coming in has to be the sum of those two. We just add them up, which gives us our answer for the total source current, about 8.33 amps. So that's it. That's the total amount of juice the battery is supplying to the whole circuit. But are we done? Not quite. A huge part of engineering is not just getting an answer, but being sure it's the right answer. So we're going to do a final check. And to do that, we're going to use our last tool for today, Kirchhoff's voltage law, or KVL, to make sure all our math is solid. So KVL is kind of like KCL's cousin, but for voltage. It's another conservation law, and it says that if you go around any complete loop in a circuit, all the voltage from the source has to get used up by the components. So for us, that means the voltage drop across each of our resistors should equal our 10-volt source. And here's the proof. Let's look at loop 1, the path through R1. We can find the voltage drop using Ohm's law again, just rearrange it. Voltage equals current times resistance. So that's 5 amps times 2 ohms, which is 10 volts. It matches our source voltage. Check. Now for loop 2 through R2. We have about 3.33 amps times 3 ohms. And what do you know? That's pretty much exactly 10 volts too. Another perfect match. Since both loops check out, KVL is satisfied. Our calculations are correct. We can be confident in our answer.
Okay, let's wrap this up by putting everything we just did into a nice, simple toolkit that you can use on other circuits.
So here are our final answers, all in one place. We found the current through R1 is 5 amps, the current through R2 is about 3.33 amps, and the total current from the source is about 8.33 amps. Awesome. But more important than the numbers is the method. These are the 3 essential tools in your toolkit. Use Ohm's law when you're looking at just one component. Use KCL when you get to a junction, a place where the current splits or comes back together. And you use KVL to check your work by looking at any closed loop. If you can remember what each one is for, you can analyze tons of different circuits.
So there you have it, a really clear step-by-step method that you can use again and again. You look at the circuit, you use Ohm's law on the individual parts, you use KCL at the junctions, and you double-check everything with KVL. That's the system. You've got the toolkit now. So the only question left is, what circuit are you going to analyze next?